Okay, so I'm gonna spend probably about half an hour running through a bunch of things that we're doing in what we call our AI lab at Autodesk. So we've built a set of labs. One lab is in San Francisco, the other lab is in Toronto, where we're researching and developing a whole bunch of AI techniques in a whole variety of industries that relate to Autodesk. So for those of you that don't know much about Autodesk, obviously this building pretty much represents a very large part of our company, which is our media and entertainment business. We also serve the mechanical engineering and electronics business, the product engineering, aeroplanes down to iPhones and that kind of thing. Those people are doing design, they're doing mechatronics, they're doing this kind of thing. So we are building products to serve those sort of industries. And then construction is one of our most massive businesses. So I can guarantee you every single person in this room has been in a building many, many times. In fact, probably most buildings you've been in have been designed in our software for many, many years. So that's a huge industry for us. All of these industries are being entirely disrupted, as you can probably guess, by AI right now. So this is very, very much strategically in the middle of what we're doing at Autodesk, which is why it's so important. And this is why we've created the AI Lab. So the AI Lab is a centralization of our efforts around researching and discovering new methods that we can apply in these industries. So I'm hoping tonight to sort of inspire you a little bit around how we're doing this and how we're thinking of this. So let's start off with a little sort of observation. And I like to start off with this because it gives you a sense of how we're sort of globally thinking about the effects of AI. So now let's imagine a fictitious scenario where everybody in this room, for whatever reason, had never ever in your life seen a hammer, and you'd never seen a chisel. You had no idea what this, never seen it, never even heard the word before. And you walked into a room and you saw some guy doing that. I'm sure pretty much every single person in this room within about 15 seconds would be able to do the same thing. You might not do it as well as he's doing, but you could probably chip away a bit of wood, and you kind of get the idea, even without somebody having to literally explain to you what these things are for. So human mind is pretty incredible at doing those things. So, here's one way I want another lens I want to put on this. So look at these two axes. There's an axis at the bottom here that talks about machine sophistication. So the sophistication of a machine. That's kind of a stretch to think of a hammer and a chisel as a machine, but it kind of is. It's a super basic machine, right? Very, very low complexity of that machine. Very, very, very simple. Also, there's another axis at the top there, right? Which is the axis of human learning. Now, good news. As we said, 15 seconds to pick this up. The human learning curve is also pretty low. So that's great. We've got that. Now let's move forward. You're going to do something a little bit more advanced. We're going to get to a wood lathe. Now, if you walk into a wood lathe, a room with somebody using a wood lathe, and you know nothing about it, I know what to do. This looks easy. It's a spinny thing, and I just sort of grab the chisel-y thing, and I stick it into the spinny thing, and something happens. And next thing, the chisel goes flying in the air and hits somebody in the head, and it's not easy, right? Or you've got to understand the grain direction in the wood. You've got to understand the spinning rate of it. Sure hope you remember to oil the motor, because it's going to die after a week if you don't do that. Suddenly the machine got more complicated. Now, yes, you can do more with this. You can make a better piece of turned wood, but the learning curve is increased. So machine increased, learning increased for the human. Now, we move forward. We get to a 5-axis CNC wood milling machine. This takes a 2-week course before you can do anything. Yes, you can make almost anything. You could carve out a chair. We've got one of these in our Pier 9 facility in San Francisco. People carve out entire pieces of furniture from one of these. They also spend a month figuring out how to do that. Right? If anybody here who's written G-code for one of these things, it's not trivial, right? So massive complexity of the machine, massive increase in human learning. So now this sort of reduces the accessibility of these things. So where are we going to go? What's happened? What's going to happen after this? Well, here's what I think is going to happen. The machines are going to continue to get more complicated, but humans are going to top out at some point. There's only so much learning a human can do. There's only so much pace of change a human can tolerate. So if it takes 2 weeks to learn something, and the pace of change of something becomes shorter than 2 weeks, guess what? You've hit what I like to call the unsingularity. Right? This is not the machines becoming super, super clever. It's the humans suddenly going, oh, geez, can't learn anymore. We're at the limit. Okay? Now, here's the good thing. I actually think it's going to come down, and I'm going to explain to you why this is going to come down. Another way to think of this blue and orange curve here, the blue is the curve of doing. Machines do stuff. right? They cut wood, they cut metal, they weld things, they're doing things. The humans are the ones doing the thinking. So the orange curve is kind of the thinking curve, which is increasing. We never blend those curves. We make a machine that's more complicated, but we put the burden of the thinking onto the human being. Always. That's the history of technology, right? It's the state of the world that we live in today. What's going to happen in the future is AI is going to appear. And an interesting thing begins to happen. There's a factorization of thinking and machines. Thinking and doing begins to blend a little bit. And the machines now over here begin to take on some of the thinking. So that future crazy machine that cuts absolutely wacky pieces of wood, but you can walk up to it and talk to it. And say, hey, I kind of want one of these, and I want it to sort of look like this. And it goes, go, okay, no problem, I can do it for you. That's the future. And this is why I'm so excited about AI and all the things we can do at Autodesk, because it's going to allow more humans, more people in the world in a more accessible way to actually get to technology and leverage it to create amazing things in the world. Okay, so now what I'm going to do is we're going to transition, and I'm going to talk about this through 4 lenses. So in our AI lab, we're thinking about this fundamentally in these 4 ways. So the first thing that I'm very excited about is this notion of dissolving the human-machine interface, because we talked about just about humans and machines, right? It's about how we come together with machines. Now, many of you in the room, I think this is, certainly I've spoken to many of the researchers here, I'm sure this is not a new concept, but there's a lot of some interesting examples. So, I mean, you look, we've got the wrench guys here, this is the Facebook deep, it's not playing, that's weird. There's the dense pose stuff from Facebook. Wrench stuff in real time, you can take a video signal and convert it into pose data in real time. So you take in something that is a raw video signal and turn it into real-time semantic information. That's pretty incredible. Then you get to, oh, there it is. There's all the people going. Then you get to, this is Modiface, a company actually in Toronto, startup. You've just been acquired, actually. It's an augmented reality mirror. You're doing your makeup in the morning, you stand in front of your mirror, the camera recognizes your face, starts to project different eyelashes, different skin tones, it can change your hair color, it can simulate contact lenses, can do all that. But what a beautiful user interface, right? There's no keyboard, there's no mouse, because you've dissolved the human-computer interface. It's at that time you need it, you're in the bathroom. This is a company, a startup in, I think down in Silicon Valley. They've built a micro radar. So it can detect very, very accurately, very fine finger movements in a radius of around about 10 meters from the surface of the radar. So in the future, you can tune devices and interact with things just by putting your fingers over that device and moving your fingers in subtle ways. So imagine a future radio that you can tune like that and a watch that you could change. Again, dissolving the human interface. Wouldn't have been possible without modern AI. And then the Glowforge, which is the world's first home laser cutter. In fact, I have my Glowforge sitting at home in a box right now. I haven't yet opened it. I'm very excited to do it. But I have a daughter who actually doesn't really like playing with CAD software, but would love to cut things out in a laser cutter. Good news, with the Glowforge, you draw on the object you want, toss it into the Glowforge, the camera picks it up, figures out the outline, and starts cutting it. You didn't remember, think of that. I mean, we certainly don't let kids use our laser cutters at Autodesk. We'd have kids with no fingers, right? You just don't do that. But with the Glowforge, it's made it simple. It's lowered that interface. It's taken some of the thinking on. Anyway, so hopefully that gives you an idea of what I'm talking about. Now, imagine this is going to be done in the world of design. So what's going to happen there in the world of design? So the one area we're looking at from a research perspective is conceptual design. Conceptual design is really interesting. Whether you're conceptually designing a car or you're conceptually designing a building, this is the time when stakeholders come together, people that are interested in that object. What is it going to look like? How's it going to feel? What's the building going to be like? They're often not designers themselves, but they have an opinion on the design. They want input into it. So you can't just build traditional CAD software because nobody's going to either know how to use it or want to use it. So this is an opportunity to begin to break down that interface. So I'm going to show you a little scenario here of how maybe a future chair designer might work.
Okay, Autodesk, I want to design a chair.
Here are some popular chairs. Scroll through them and select some examples to give me an idea of the type of chair you would like.
Okay, I'm making some selections now.
Notice the amount of information you're conferring by selecting examples.
Okay, combine all possible pairs between these 6.
All right, there are 15 possible pairs. and morphing the form between all pairs, generating a large range of combinations. Here are 5 design possibilities between each of the 15 pairs. There are a total of 75 possible designs.
Okay, great. That's a lot of options. Let's go back to my original selections and I'll just direct you step by step.
Okay, here are your original selections.
Okay, combine these two.
Alright, here are 11 options between the pair you selected. There are 2 repeated sets to show both original leg styles. Scroll through them and select one to make further design changes.
Note the AI is semantically altering the chair, not just in terms of its geometry, but the semantics of the chair.
Here it is.
Show me the other leg options with this chair.
Here are the 6 original leg styles adapted to this design. Select any style you would like to use.
Okay, switch to this one.
Okay.
Make it wider.
It understands parameterization.
Not that much. Split the difference.
Reducing width 50%.
Make it work for a really tall person.
Alright.
Lower the top of the back to this red line I'm drawing.
Okay. Here you go.
Okay, make it into a lounge chair.
Alright. Matching to the parameters of a non-lounge chair with high user ratings for comfort.
Show me a comparison of the two.
Here you go.
Make the chair look good inside this space.
Adjusting materials to fit in with the environment you uploaded.
All right, make the materials look like this outfit.
Alright.
Right, we'll stop there. It gets a little crazy now. If you were in a studio somewhere with a chair designer and you were wanting a chair, you'd probably be having sort of a similar conversation. You know, I want that, sort of like that one out on the showroom floor, but with a little bit of that one mixed in. And I like that leg style over there. And it's too tall, make it shorter. And, you know, this is what my living room looks like. Do you think it could, what materials would you choose? This is exactly how you would interact with another human being that was designing for you. So this is a powerful clue as to how we can design software in the future that's AI-powered. Sociology and anthropology is actually going to become a much more significant field of study in designing human-computer interfaces in the future for this very reason. So what I'm going to do is quickly show you some of the research we're doing related to this. Now, one of the core things we want to do, obviously, to do that kind of thing that you've just seen is synthesize geometry. So creation of different forms of geometry, control of those is significant. So, you know, one of the most obvious things to do is to take a 3D model, to voxelize it, and you begin to train a neural network to understand a voxelized model. That's pretty basic stuff. The problem is most of you who are in computer graphics in this room know that voxelized models are not small, so you tend to reduce your resolution of voxelized models. When you run them through a network, it tends to explode the size of your activation layers. Also not a good thing if you want networks to converge in different models, right, later on. So, you know, you can do it. You can get a classification out. You can get some sort of embedding out. That's kind of the old way of doing it, right? Then, you know, a new thing came along a couple of years ago, which was the multi-view convolutional neural network. So this is kind of a simple idea, but it actually works amazingly well. Is that you basically take 20 images of the model at fixed distances and directions around the periphery, and you rotate each of them, so you end up with 80 images as well. You take them through four 90-degree rotations, and you feed them into a network, one after each other. So you take each of the 80 images, so you do a cycle of 80, and after you've cycled 80, there's this triangular piece over here that I call batch max. What you do is you basically do a max pool across all 80 of the receptive fields at that point in the network. So you kind of smush all the information together if you want. And then you push it through the rest of the network, and kind of what the network's doing is it's basically projecting knowledge from each of those 80 vantage points and coming up with some synthesized global sense of what the object is. Turns out it actually works pretty nicely. It has this horrible problem, which is the triangle, which is the fact that you batch maxing things. Because when most people that I'm sure are in the research here know, when you max pool things, you're selecting the maximum. So you're throwing all the other information away. And that's going to be a problem, because later on, if we're going to try and turn this into a generation network, into a decoder, you can't decode backwards through something like that. So you need to change the network in a fundamental way. What we discovered with this a year or two ago was you could throw away that triangle and replace it with this tiling operation. Now, as most of you that are aware with CNNs are about moving a kernel across a space. So there's naturally a translation invariance that occurs inside a CNN kernel, or with a CNN kernel. What you can do here is you can actually take the 80 little images. Instead of maximizing them, you build one long strip. So you end up with a strip of 80 times the length of an individual image. And then what you do is you run that through 3 more convolutional layers that progressively reduce it and process it together. Now, because of each of the 80 images are effectively rotations, and convolutions are translation invariant, what you're doing is you're turning translation invariance into rotation invariance, because it can just move through it. So it actually works very effectively. It also has the great bonus of being reversible, so we can actually backpass through that and turn this into a decoder. Some examples of this kind of images that go into it, the 80 projections. But now we want to make this into it. Like I said, we want to synthesize geometry. So what do? You heard Satya talk of his Ian Goodfellow story. This is the home of GANs. So you start off with a AC GAN. It's a categorical GAN. So what comes in is the class of an object, your stochastic variable. You run a network that's the network I just showed you, but notice it's in the different direction now because it's a generator network. It's a decoder network, right? So it's actually synthesizing 80 images of a new object from 80 directions, right? So it might produce an image like that. You're going to feed it a real image. You're going to train a discriminator against it, and you're going to use the discriminator as the loss, and you're going to iterate, right? Standard GAN architecture. So it turns out this actually works reasonably well. When you have one class, it actually synthesizes 80 pretty decent images of a bolt, and you can actually resynthesize a 3D model from it. Of course, when you go to many classes, you start having stability problems. And as many of you are aware, this is the story of GANs, this mode collapse and various stability issues, right? And because you're dealing with such a large input field, it tends to push the GAN into these spaces quite a lot. So this begins to fail. Then what you can do is you could try the same thing with the voxel approach before. The problem with the voxel approach, like you remember me saying, is the activations are massive in these. So this actually makes the GAN actually even more unstable. But if you stay within certain classes, it actually works quite well. This is the GAN generating aeroplanes. These are just unique sort of aeroplane models that it's generating. It's actually not bad, but again, notice the low resolution, right, of those aeroplane models. If you kick up the resolution, these things begin to fail quite badly. Then what we started doing is looking at a variational autoencoder, which actually works way better. So now we've taken 2 of the same networks, your generator and your encoder and your decoder. We're introducing a random vector, and you've got a latent space in the middle. This turns out to generate actually reasonably good things. So these are some examples of chairs and airplanes and guitars, all synthesized using the VAE. And it's pretty stable and very coherent, the 80 images. We can synthesize nice 3D shapes from those using shadow carving techniques, and you can see some of the clustering there of that sort of centralized embedding space. It's actually pretty good. It also works out that you can do some of the usual things you can do with a good embedding space. We can do geometric operations on it. It's got an algebra, it's got a grammar there, so we can subtract roundedness from a vase and produce a straight vase with a rounded top and fiddle with tables and do things like that. Now, where we're going with this is we're going into point clouds. So it turns out that one of the best ways to actually deal with models is not through voxels, it's not through images, it's actually through random sampling of the point. So if this microphone I'm holding was the object, you would basically randomly select points all along the surface of it, really literally maybe 1,000 points, for example. It turns out those 1,000 points are a very stable way to reason about the geometry of this thing, and the networks work very, very well. So the PointNet architecture, which is developed out of the Guibas lab at Stanford, is a lab we work with very, very closely. And then PointNet++, which is a sort of a more hierarchical version of that, works very, very well for these. And where the research is going now, which we're working on with them, is using GANs, again, going back to GANs, but using GANs to synthesize point clouds right now. And because the input layers and the activations are actually less in this case, you're sampling just like 1,000 points, for example, and you're generating just 1,000 points, these networks tend to be a lot more stable. If anybody's interested, I can tell you more about this later on. We actually use a combination of a VAE with a GAN embedded in the middle of the VAE, because the VAE reduces the latent space so that the GAN is working on a smaller vector field when it comes in, which stabilizes it. Anyway, so that's enough of the technical talk on that one. The other thing we do is we do a lot of simulation work. If you're building chairs and you're going to make a chair, the chair's got to make sense, right? The chair's got to stay up. You don't want tiny, thin little legs that'll break when somebody sits on it, right? So simulation is a big part of this. So the other thing we're doing a lot of work on is surrogate modeling, learning, machine learning models. They're combinations of sort of new mathematical principles, new computational science principles combined with AI to learn. So in this case, this is a finite element simulator. So this is basically a rod that you could imagine is attached to a wall on one side, and there's some pressure being placed on it, so it's going to sort of bend in some ways. In a normal sort of stress simulator, that would take like 10 minutes or so to do a good simulation on, which is obviously far too long for an interactive system. This can infer in about 50 milliseconds what's the stress loads on things and how it's going to perform. Again, a key piece of building the right thing and doing it automatically. This is a real-time computational fluid dynamics system. As I'm tweaking the system, it's computing new flow lines. It's able to, it's effectively, in some ways, an approximation of the laminar flow state of Navier-Stokes equations. All right, so that's dissolving the human interface. Let's talk about learning from the past. When you look at designers, when I spend an enormous amount of my career with our customers, be they architects or engineers, looking at how they design. And one thing always strikes me, when anybody designs a new thing, they pretty much start from scratch. They never look at what they've designed before over the last 40 years of a building or whatever it might be. Why? Because it's generally too hard. It takes a heck of a long time knowing what you need to bring forward. So learning from the past is something that AI could really help designers with. So I spoke about this last year when I was here. We built something called the design graph that mines literally every design you've ever created, brings out the geometries, it interprets those geometries in terms of the shapes of them. It understands the topology and the shape variations and the features of these objects and can reason about what's similar, what comes together in common systems. It can reason about the subsystems of components, and it can generalize them, and it can build a knowledge graph like the one you're seeing us fly through over here. So now when you're creating a new thing or you're drawing a new shape, the software can say, hey, it looks like you're making one of those. When I've seen people make those, there's other components that go with it. Let me help you go through your catalog. Let me find you the ideal components to use. It really is kind of bringing forward the knowledge that you sort of encoded in all of your previous designs in some way. So that's a big part of learning from the past. The other thing we're doing in this space is we're also trying to understand individual objects. So if we just get a point cloud like that of some component, could we understand how that object varies? Because maybe this is a generic component that in different stages, some pieces are wider or they're longer, or it changes in some parametric way. So what we want to do is discover the latent parameterizations of objects that we've never seen before. Could we do that? So that's a large part of our research as well. Doing that, one of the ways we're approaching that is by fitting Euclidean geometry, so cylinders, similar, boxes, just sort of standard shapes to these, which have trivial parameterizations. We know the parameterizations. Once we've fitted them, though, we can learn the co-parameterizations of those. So, for example, a table, you can fit 4 cylinders to the legs of a table. Generally, tables have the same length legs, right? AI doesn't know that, but if it sees enough models, it's going to notice that there's always 4 cylinders that have a trivial equality relationship between the height variable of the legs. So you can actually learn these parameterizations, and it turns out often those are very, very mean, especially the co-parameterizations are the things that are meaningful to human beings. The next one I want to talk about is thinking beyond your brain. This is one of my favorites. And, when you watch a designer work, this really brings it home to how, in some ways, amazing humans are, and in some ways, how limited humans are in their design ability. So imagine, if you will, everybody in this room, you're a designer in a company, and your boss has just come into you and said, I need you quickly to design me a bracket. So here's the problem. There's an I-beam that goes through this building, and we've done a sectional slice through the I-beam here. The I-beam's got this little piece of metal that juts out of it. It's welded on the side there. And there's a piece of conduit that we need to attach to this I-beam, that sort of rectangular curve, rounded rectangle over there. You need to design a bracket that sits inside this sort of red area, right? You need to to design something that fits into that. So what do you do as a designer? Well, you take your idea and you start to think of the solution. Now, every one of those purple dots there represents a potential solution. It's the solution space. And as a designer, you start going through that solution space, and you use your training, and you use your history, and you use the guy in the office that's done brackets before, and you do a whole bunch of things, and you come up with 8 solutions at the end of the day. And you know what? You're feeling pretty good about your 8 solutions. This is great. You've got 8 solutions. Of course, you've missed out on all those other ones, but you're feeling good about the 8 solutions. Why did you miss out on those, and why are you feeling good about it? Well, this is where human bias comes in. Human bias is an amazing thing. Human bias is kicked in all over the place, and it was the thing that stopped you from going into those things. So, I'll talk about something like, say, the anchoring effect. So anchoring effect is something where the very first design you produce, the very first one you made, always kind of feels, just in the niggling back of your mind, like the best one. That first one you got, it's the same feeling as you get when you go into a clothing store and see a shirt or a jacket or a pair of jeans. It's the first one you saw, and then you keep going looking at other things, but there's a little part of your mind that's telling you that first thing you saw is probably the one you really should buy. That is absolutely the anchoring effect kicking in. It's this documented common human bias, massive in design. All sorts of, there's a nice codex online of all the 184 human biases that can kick in during these kinds of things, right? So how could we get somebody out of that? Imagine if we could compute that bracket. Imagine if we could actually understand that you were trying to attach a piece of conduit to an I-beam. What if we could simulate every possible thing that could be done in that space and use, say, a topology optimization algorithm to discover things? Now, a human being would probably not design maybe any of those, but they're all actually excellent solutions. In fact, they're all close to optimal solutions. And you think 15 is pretty nice. We had 8 before, we got 15. There's not 15, there's thousands. Right? So it's showing you that space. It's exposing you to all those purple dots, right, in that solution space that you weren't aware of. So you can almost think of some of this as like a debiasing algorithm. It's sort of exposing people to solutions that you wouldn't otherwise come up with. Now, any of you that were concentrating, you saw the title of my talk at the beginning, Humans plus AI equals the future of design and make. And this is the epitome of what I mean. The best of humans. Take human creativity, take human empathy, take human understanding, but bring it together with AI and computation and allow it to actually discover things that we wouldn't by ourselves. This is an example of an interface we have to move through a simulation. So it's running, so you're trying to design a computer monitor stand. It's producing thousands of options. And what you're doing is you're selecting the primary parameters, the weight characteristics, volume, all sorts of things about that stand. And at each point, it's trimming that solution space down to probably the solutions that are close to the kind of performance and characteristics that you want. You're not done with the design yet, but it's at least got you very close to something that has the characteristics of what you actually need in a design. This is going to be a new way we're going to see people designing in the future. The last thing I'll share with you tonight is make like never before. So everything I've spoken about is how you design something. We're going to create something. And at Autodesk, we're very, very serious about how the world of making is transforming, because design and make are coming together. You don't design something today without thinking about how it's going to get made. What's the impact and what's the method? There's a tight sort of feedback loop between these. So if you go into a factory today, a factory looks kind of, most good factories look something like this. Now, I'll tell you a story. I was visiting one of our customers last year who has a factory. It's not this factory, but it's similar. And it's as clean, if not cleaner. You could literally eat your dinner off the floor of this factory. It's absolutely perfect. Everything's exactly in the right place. Everything's... Now, we did a tour of the factory, and we sat down. I was super impressed with this, blown away, in fact, by the factory. We sat down afterwards, and the head of the factory group said to me, we really messed up with our factories. We've really gotten ourselves into a tight spot. Really? It doesn't look like, it looks like an amazing factory. And he's like, yeah, that's exactly the point. If you look at this factory, everything has its place. There's a perfect place for that car door. There's a perfect place for the shell. Everything has to be positioned in those places. The factory is deterministic. It's designed to be absolutely predictable because every system in there relies on that predictability. That's good. It means their failure rates are low. They can produce a lot of cars very reliably. What it means is they also can't produce a different car very easily. A factory like this takes nearly a year to just be basically reconfigured for a different design of a car. So you've kind of given up on flexibility for reliability, because that's the old world of doing work like that. So, robots like these are super impressive, but, it takes 9 months of system integrators to configure a set of robots like that to do spot welding on cars. And great, if one of those cars comes in 2 inches short on the line, guess what? All your spot welds will be 2 inches short because the system's completely unaware of what's going on. It's assuming it's a deterministic environment. So how do we move to a future environment where robots could be undeterministic, where humans and robots could interact? What if the robot sensed us? What if the robot had an AI model of how humans move? If it could actually reason about how not to hurt you and how to work with you? So this is where we're going with a lot of this. So our project here is a project called LegoBot. For those of you that were here last year, I think I spoke about the very beginnings of the LegoBot project, and I'm happy to say we've come a lot further from where we were last year when I spoke about this. But the idea is to build a robot that can learn to build Lego by itself. Not be programmed to do it, but learn to do it. So it can go from a bin of bricks, and it can learn to pick up those bricks and start building something much like a child would. Now, it turns out that's actually a really not trivial thing to do. We're going to base it purely on two things. We're going to base it on a camera that's sitting on the edge of the robotic arm, and we're going to base it on a torque sensor that gives us a 6 degree of freedom force feedback. So we can touch and we can see in a very simple way, right? And we're going to have it learn. But the way we're going to make it learn is different. We're going to actually teach it in a digital environment, because teaching a robot physically is not a good way to go, because robots tend to be kind of slow. You can pick up one brick every few seconds, maybe. In the cloud, we can do this thousands of times over. We can simulate this with digital models of Lego bricks. We can simulate the physics. We don't do it once, we don't do it 4, we don't do it 8, we don't do it 16. We do it thousands of times in parallel in the cloud. So in one evening, we can generate 10, 100 million samples of data of how a robot might interact with specific Lego bricks, with specific tasks in mind, like recognizing something, disambiguating something, pushing something out the way, picking something up, turning it over. All those operations, you want to learn them from scratch, right? So that's how we do it. Now, in the real world, obviously, our real objective here is not to sell a product at Autodesk that builds Lego. Our idea here is to revolutionize industrial robotics, right? So now imagine if you were a designer in a company that had designed some new thing for a car. You've checked your model in on a Tuesday night. You're going home now, you're done. You go home, the system picks out that digital model, starts to run all the simulations, right? Runs all the things that the robot needs to do. By the time you come in on Wednesday morning, it's uploaded a new inference model to all of your robots that can now see, recognize, understand, grasp, and interact with that object. In one night, your factory reconfigured itself to work with something new. So this is starting to get to the kind of factory that we're talking about in the future. So here's an example of the networks we are using here. So we use an end-to-end fully convolutional network for a lot of our pose and object understandings. We tend to use the network directly to understand grasp points. So grasping something is not just about knowing where to put your fingers, but it's also about knowing the nature of the object. It's also about knowing the neighboring objects. So for example, here you'll see the red lines are the grasp points there. It didn't try to grasp the middle brick because it knows you can't grasp the middle brick because there's 2 bricks to each side of it. So it's actually understanding the environment around the bricks as well. It's really learns a lot of kind of interesting stuff. We then have to learn about translation, how to translate the brick. You notice it's turning the brick over there. It learned how to do that by giving it a whole bunch of signals of bricks at different angles, trying out different techniques. So we train it on how to do that. The other thing you'll notice is we have this little end effector, which actually has a little Lego brick actually stuck on the end of it. One of the problems is when you're going to bring down a Lego brick, holding it by its sides and trying to click it on turns out to be not very good, especially if there's a brick right next door, right? It's the fat finger problem. It bumps into the things. So it turns out it's much better to actually use a little Lego brick on the end, click something in, and then roll it off into places when you're placing it. So this has led us down a whole nother research area, which is different forms of specialized end effectors. Also, if any of you have ever tried to put a Lego brick exactly vertically on top of another brick, it's really hard. It's super, super difficult. There's a 0.1 millimeter tolerance on a Lego brick. So we have yet another network which actually deals with visual servoing based on a UNet that does micro adjustments as it's like coming down into Lego bricks. So we've learned a lot about this, but this is the robot in action here. It's able to pick up bricks, recognize them, grab them, place them. This is obviously, again, what the camera is seeing. You'll see it doing various things. Some of the bricks will rotate automatically if it needs to, so the arms work in tandem. This is it, just speeding it up, kind of building a little tower here. It doesn't care about color, obviously. It builds it pretty nicely. This is a little shrunken example of the Transamerica Pyramid in San Francisco. There we go. Now we're now in the research working on non-rectangular bricks as well, so we're starting to work on more complex shapes, which is, again, why we chose Lego, because Lego's got this nicely graduated curve of complexity. You can just choose different components as you go. And now where we're at is actually 6 degrees of freedom bin picking. So now you'll notice in all the examples I showed so far, everything was nicely laid down on a table. But we really do want to deal with a bin where things are obscured, things are at angles. And you'll notice our researcher in a moment is actually going to bring his hand and he's going to move some of the bricks around and put them at funny angles. But now the network's not just learning how to grab things, but learning about the angles in which to come at into the bin and reason about what's in its way, what needs to be moved first, what can I grab later on. So it turns out this thing can actually do that very, very reliably. So we're very, very close, I think, to our first large-scale industrial experiments where we can actually start putting this into factories to work with things. So I'll finish with just a statement about the AI Lab. So we have 2 AI Labs, one in San Francisco, one in Toronto. It's a group of researchers that work together on all the kinds of things that I've shown you, as well as a lot more. I didn't have time to talk about a lot more of them. But we work closely with the product groups. We do coupled research. So we work with academics. We work with students that come in. We develop research papers and directions. But we also have the engineers from these product groups that sit in the lab with us to turn these ideas into real life kind of projects and anything. So if anybody here is interested in joining us or working with us or an internship, we do a whole bunch of things. You know, there's a set of little Join the AI Lab cards at the front there. Drop us an email. That goes to all of us in the lab when you send it to us, so we'll hear from you. But I'd love to hear from some of you. Thank you.